Hey team, hope we're all doing well. In this video today, we're starting to look at using matrices in transformations. I wouldn't say it's more complex is the right word. I'd just say it's a little bit more abstract how we're going to just using matrix. It's still coming down to the simple transformations of we are translating, we are dilating, and then we're reflecting, but we can represent these transformations with matrices. And if we can represent them with matrices, we can then do matrix operations on, say, coordinates and find out what our original coordinate, what is it transformed into. So that's what we're going to start moving towards today. So our learning intention is to use matrices to represent and apply transformations. And our success criteria is to write a series of transformations in the form of a matrix, and also then to be able to apply these transformations represented as a matrix to a set of coordinates. So at the moment, we're not applying them to functions, a full equation. We're just transforming sets of coordinates, and we're going to use matrices to do that. So let's get going. Okay, so a bit of refresher, really quick refresher, is some matrix operations. If we're matrix multiplication, if we're multiplying a 2 by 1 by a, it should be a 2 by 2 by 2 by 1, the other way around. We just need to remember that we're taking the rows of the first matrix and multiplying by the columns of the second matrix. So a quick example here, we have 1, 0, 0, 3, blah, blah, blah. So this top bit here is the first row multiplied by the first column, and then this is taking the second row multiplied by the first column, gives us that, and then it's just simplifying from there on. If you're a bit fuzzy on the whole matrix operations, you're going to have to go back and review them yourselves. That's not the purpose of this video, but just to give you a bit of a warm-up to think about it. So 1 by negative 2 is negative 2, 0 times 1 is 0, 0 by negative 2 is 0, 3 by 1 is 3, so we get negative 2, 3. So that's a 2 by 2 multiplied by a 2 by 1, which are generally the bit easier ones. And then the harder ones are the 2 by 2s multiplied by a 2 by 2. Same thing, first row by first column gives us top left. First row by second column gives us top right. Second row by first column gives us bottom left. And then second row, second column gives us bottom right. So if we do this example here using these numbers, we get that and that, and then we just got to simplify. 1 by negative 2 is negative 2, 0 by 0 is 0, 1 by 0 is 0, plus 0 by 1 is 0, so 0 and 0. Same down here, we get 0 and 0, and here we get 0 and 3, so negative 2, 0, 0, 3 in that case. A little bit of an odd looking matrix, but that's the way it works out, partially because there's so many zeros in the original two matrices. But that's a little bit of a refresher just on matrix operations, which we're going to need in a little bit. Like I said, if you're a bit fuzzy on it, you're going to have to go back and review it yourself. Right, okay. This is the list of ways that we can write all these transformations we've been dealing with so far, or actually, sorry, I should say the reflections and dilations, and then there's this new one when we're reflecting about the line y equals x, which is instead of reflecting about the x-axis or the y-axis, we actually flip about this axis, which is just the same as actually finding the inverse. So that'll come in handy a little bit later. But we can represent all of these where we can think if we're reflecting in the x-axis, well, the new x-coordinate is the same as the old, but the new y-coordinate is the old y-coordinate inverted, so multiplied by negative 1. We just think about reflection. Same happens if we reflect about the y-axis. If we're reflecting about the y-axis, it's actually the x variable gets changed. That's why there's a negative x there. And this pattern keeps going on. If we think logically about what a transformation is, so if we dilate by k from the y-axis, y-axis is up and down, we're stretching away. What's the actual coordinate that's changing is the x coordinate, and it's changing by the factor k. Now, these rules shouldn't be too complex to think about or how they're formed. You don't need to remember these rules themselves. What we need to actually remember is these matrix representations of those transformations. Now, I could go into how we turn these two equations into this matrix, but you don't actually have to be able to do that yourself in the course. This is a version of effectively inspection. So the way I remember it is I think of these 2x2 transformation matrices as x and y in the top left and the bottom right. The top right and the bottom left, they're a little bit weird. We can ignore them apart from down here for this reflection in the line. We just need to remember that instead of dealing with the x and y, we're putting ones in the opposite corners, which is effectively flipping our x and y variables. But the way I think of it, the way I remember, and PowerPoint is possibly crashing on me. Oh no, it's come back. Is my x coordinate is top left, my y coordinate is top right. So I then think intuitively and logically, if I said, oh, well, if I'm reflecting in the y-axis, what's the variable actually changing? Well, it's the x variable actually changing, so it becomes negative. So I put a -1 there. Same for, say, if I did a dilation of factor k from the x-axis, so k some number, whatever it is. Well, if I'm dilating from the x-axis, what coordinate is actually changing? Well, that's my y coordinate that's actually changing. How much is it changing by? Well, it's changing by k. So I put a k there instead of 1. So the standard, I guess, no transformation matrix, or the original equation or coordinate stays the same as the old, is just 1 and 1. Okay. That is no change. So if we then build off that no change, well, okay, if I'm reflecting the x-axis makes my y, that changes into a negative. Or if I'm doing dilation by factor k from the y-axis, what's actually changing? It's my x variable. So instead of 1, I turn that into a k. So if you think of starting with 1 and 1, top left, bottom right, and then think of what the transformation is from there. Here we go, 7 minutes in. Okay. So, for example, if we have a dilation of 5 from the y-axis, so that means that is actually affecting the x coord. Okay. Well, then I'm going to change, instead of 1, 0, 0, 1, instead of changing, I'm going to change the 1 to whatever the dilation factor is. So that's going to change to a 5. So it's affecting the x coordinate. So we can say that's our transformation matrix, or our dilation matrix, because we're just only applying a dilation. We can also then say whatever our original coordinate is, well, our original coordinate is just x and y, we can write it as a matrix in that form. We want to store it. Okay, we're storing our coordinate. If we could think of this maybe computationally, like a computer's doing something, well, they're going to store a coordinate in a matrix that looks like this. Okay? Or a vector technically, but we'll just call that a matrix. And then we want to find what some new coordinate is. By applying transformation to our original one, we can actually write it out like this, where we take our dilation matrix, multiply it by our original point, and if we then solve that matrix operation, we will find the coordinates of our new point. Hence why we had this refresher here, because what this is going to be is our transformation. This is going to be our original coordinates, whatever they may be. And then once we get our answer, doing all that working out, this will be our new coordinates. So we can work through that. Now, the order is really important. You must put the we call it dilation in this case, but you must put the transformation matrix first, or the dilation or reflection matrix first, then the coordinate, because that's the only way you can multiply those two matrices together. Because remember, we're doing a 2 by 2, which will be our dilation matrix, and that is being multiplied by a 2 by 1. And if I did it the other way around, these two inside numbers wouldn't match. Remembering, to multiply matrices, these must be the same number. So, let's have a go. Find the image of the point 1, negative 2, so that's our original coordinates, under dilation of 3 units from the x-axis. So, I'm just going to put 1, 0, 0, 1 in here, and then I'm going to think, what do I need to change it to? Well, I'm dilating 3 units from the x-axis, so that means I am affecting, actually, I can't spell today, affecting the y-coordinate, and I'm dilating by a factor of 3, so I need to actually change my y affecting part of my transformation matrix to a 3. My original coordinate was up there, so that's just a 1, negative 2. So what is that going to equal to? I'm going to get some matrix where I have to multiply the rows by the columns, so I get 1 by 1 plus 0 by negative 2, and I also get 0 by 1 plus 3 by negative 2, and that's going to give me as a matrix 1 plus 0, 0 plus negative 6. So I get 1, negative 6. So my new coordinates are 1, negative 6, which makes sense. If we look at the actual coordinates, I started at 1, negative 2. I'm dilating at 3 units from the x-axis. Okay, so I'm stretching away from the x-axis, so my y values change by a factor of 3. I can see that that has gone up by 3. Now, you could have done just that times by 3 straight away, bit of intuition, but this was just a simple example. Once we start combining all the transformations, it becomes much more complex, hence we want to use the matrices. Okay, so we'll do this example, find the image of the point 4, 5 under reflection through the y-axis. So I'm going to start with my transformation matrix, then I'll have my original point. So again, I'm just going to put the 1, 0, 1, and think I'm reflecting through the y-axis. I'm flipping about the y-axis, that means my actual x variable is changing, or my x coordinate. So I'm going to change the x to a negative 1, as it's being flipped. Put in my original coordinates. If I do the matrix multiplication, I get negative 1 by 4 plus 0 by 5. Then I get 0 by 4 plus 1 by 5. And that's going to give me negative 4. Yes, negative 4 plus and 5. So my new coordinate is negative 4, 5. Again, we could figure that out intuitively. The x variable is being flipped from one side of the axis over to the other. So we've effectively just made that negative. Right. So that's applying in the most basic form. That's one of our learning intentions, was to apply a simple transformation matrix to a single coordinate. Now the other bit is to be able to read transformations off read transformations off a matrix that is telling them that. So again, just think of the standard node transformation is 1, 0, 0, 1. So what am I seeing? Well, my x is being multiplied by 3, so that's going to be a dilation by factor 3 from the y-axis. And then same, that's being made to a 2, so it's being multiplied by 2. So that's going to be a dilation by factor 2 from the x-axis. Matrix 2, thinking about what transformations are that has been made negative. The x coordinate's been made negative, so that means we're actually flipping about the y-axis. So we are reflecting about the y-axis. And then this one here, it's been multiplied by 4, so we must be dilating by a factor of 4. 4, and it's affecting the y-coordinate or the y-point in the matrix, so that must mean we're actually dilating by a factor of 4 from the x-axis. Last one. To go to the 5, we must times by 5, so we're dilate by 5 from the y-axis. Now, to go to -2, we need to times by 2 and then also make it negative. So we are dilate by 2 from x-axis and reflect about the x-axis. And since there's no translations here, and we'll come to translations later in another video, since there's no translations, reading, we could have done the made it negative and then the times by 2. It's not actually going to change the end result. We still get the same transformations applied. What have we got? Here's a much longer look at figuring out if we're told one set of coordinates goes to this, and then we're told also another set of coordinates has a transformation like this. Can we figure out what the transformation matrix is? And in this case, we start getting the final actual answer turns out to be something that looks like 2, -3, 3, -1. So we actually get some numbers in here, which you wouldn't have been able to figure out intuitively. So this is where we have to use the matrix thing. But we'll leave that for now and visit in class. Hope all goes well, and sorry about the late video.